In 4.2, we're going to actually dive into some basic probability rules, and I think you might like this because it's more numerical than just writing. Okay, many board games involve rolling of dice. Imagine rolling 2 die, one that's red, one that's blue. You can use the outcomes to develop a probability model. So this is a probability model. You can see that we have the 6 outcomes. If the blue comes on lands on a 1, you have all the outcomes of the different possibilities on the red. Blue lands on 2, all the outcomes possibilities on the red, and so on and so forth. So what you see here is the probability model of rolling 2 die. There's all different combinations that can happen. So again, the wording is, this is a probability model. It's a description of some chance process that consists of 2 parts. A list of all possible outcomes and the probability for each outcome. The list of the possible outcomes is called the sample space. Okay, so actually what we have here is the sample space. This is not the full model because we don't have the probability of each outcome listed. Okay, so that's the sample space. Now, the probability model does more than just assign a probability to each outcome. It allows us to find the probability of a certain event specific. Okay, an event is any collection of outcomes from a chance process. Like, how many times did you roll a 1? At least 1, 1, 1, 5, whatever. You specify an event, okay? Now, events are usually designated by capital letters like A, B, C, or so on. And it's fairly easy to find the probability of an event in the case of equally likely outcomes. If all outcomes in a sample space are equally likely, the probability that event A occurs can be found by using this formula. The number of outcomes in event A divided by the total number of outcomes in the space. Okay, this goes back to the problems that you have learned in middle school, like what's the probability of pulling out a pair of red socks out of the drawer when there's 3 pair of red socks out of 12 total pair in the drawer. You know, you put 3 over 12 and then reduce it. This is the old probability that you're familiar with, okay? Now, some rules of probability that you have to know. Number 1, the probability of any event is a number between 0 and 1. This rule follows from the definition of probability. It's the proportion of the times an event would occur in many repetitions of the chance process. So no probability is ever going to be greater than 1 because 1 is the same as saying it's a 100% chance. Okay? Can't be more than 100% chance. So probabilities between 0 and 1, most likely they're decimals. Okay? All possible outcomes together must have probabilities that add up to 1. Anytime we observe a chance process, some outcome has to happen. Okay? So if you list all the possible outcomes and their probabilities, when you add them up, they add up to 1, and I'll show you an example here in a minute. Number 3, the probability that an event does not occur is 1 minus the probability that the event does occur. And we refer to this event of not A, like if A is the event and we don't want it to occur, so we say not A. We refer to that as the complement of A, and we abbreviate it or denote it as A with a little c superscript. So here it is in formula. The complement rule says that the probability that the complement of A is 1 minus the probability of A, where A complement is the complement of the event A, that is the event that A does not happen. Okay, we're going through theory and I'll give you examples, don't panic, okay? Now, when 2 events have no outcomes in common, we say that they are mutually exclusive, all right? 2 events, A and B, are mutually exclusive if they have no outcomes in common and can never occur together, okay? That is, the probability of A and B happening at the same time is 0. So, for instance, probability of having a job and not having a job. You can't do the same at the same time. Can't happen, okay? But there's lots of other possibilities of it. Now, the addition rule for mutually exclusive events, A and B, says that the probability of A or B is probability of A plus the probability of B, okay? This is if they are mutually exclusive, meaning they cannot happen at the same time. It's impossible. Like, probability of being a senior or a sophomore. You can't do both. You're one or the other. Okay? Now, note that this rule only works for mutually exclusive events. We'll develop a more general rule for finding the probability of A or B that works for any two events that happen if they could happen at the same time. All right? Now, let's try some examples out. A four-sided die is a pyramid whose four faces are labeled with the numbers 1, 2, 3, and 4, like the picture here. Imagine throwing two fair four-sided dice, one blue and one yellow, and recording the number on the bottom of each pyramid. Okay? All right, A, give a probability model for this chance process. So remember, probability model means we list out all the outcomes and their probabilities. All right, so let's think about this. They could both land on 1, 1, 1. One could land on 1, the other one on 2. And then we'll continue with the 1 in the front, 3, 1, and 4. All right, that's 4 possibilities. Then we do the same thing with 2. Then 1, then 2, 2, 2, 3, 2, 4. Then 3, 1, 3, 2, 3, 3, 3, 4. 4, 1, 4, 2, 4, 3, and 4, 4. Now, we've listed all the probabilities that could happen here. They are all equally likely. So let's think. How many outcomes did we come up with? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? So there's 16 outcomes, and they're fair die. So we would say because both the die are fair, each of these 16 outcomes will be equally likely and have a probability of 1 out of 16. All right? We know that because it's a fair die and there's 16 outcomes. Now, B says, what's the probability that the sum of the numbers is 5? So sum means they add up to 5, right? So we look through our outcomes and we'll pull out the ones that add up to 5. So 1 and 4, 2 and 3, 3 and 2, and 4 and 1. Okay? So there's 4 possibilities, right? So that's 4 outcomes. So it's 1 out of 16, plus 1 out of 16, plus 1 out of 16, plus 1 out of 16. Okay? So we can just add these up. That gives us 4 out of 16. If we reduce that, which we always reduce it, it'd be 1 out of 4. So we write our answer as the probability of the sum of 5 equals 1 out of 4. All right? So probability model means you list all outcomes and their probabilities. Okay. Number 2, all human blood can be typed as one of O, A, B, or AB, but the distinct distribution of the types varies with race. Here's the distribution of blood types of Black Americans. Suppose we choose one Black American at random. All right? But what is the probability that a chosen person has type AB blood? Now, look at the table. They didn't give us that, right? But we know a probability property. One of the properties says that all the probabilities have to add up to 1 because everybody has a blood type, right? And so these all have to add up to 1. So to find out what that AB blood type is, we're going to have to subtract them from 1. So we're going to say 1 minus, and I'm going to add up the known blood type. Okay? And that comes out to 1 minus 0.96. So then the probability of an AB blood is 0.04. All right? So that's the probability they're asking us. And then they ask me why. Why does that work? Okay, because all probabilities add up to 1. Okay? Now, B, find the probability that a chosen person does not have type AB blood. Well, that's all the rest of this, right? Does not have type AB blood. So You could know from what we just did that it's going to be 0.096, but probability that it's not AB blood is going to be 1 minus the probability that it is AB blood, which gives us 0.96, right? So that's how you handle a complement. Now, continuing on with the same probabilities, Rolanda has type B blood. She can safely receive blood transfusions from people with types O and B. Find the probability that a randomly chosen Black American can donate to Rolanda. Well, stop and think. Are these events mutually exclusive? Can someone have O and A type bloods? No, you only have one type of blood, right? So because they're mutually exclusive, I can add the two probabilities that I need. Okay? So I can add the probability of type O blood and type B blood. So it's the probability of O or B. Type O blood is 0.49 plus type B blood is 0.20. So I simply add those up and I get 0.69. That's the probability that a randomly chosen Black American can donate blood to Rolanda. B. Find the probability that a randomly chosen Black American cannot donate to Rolanda. Okay? So since it's the complement of what we just did, we just subtract it from 1. And we get 0.31. Alright, simple enough, right? That's all you got to do. So we're going to practice this today in your homework, and hopefully that'll make a little bit of sense.